let's get started on vectors. Let's first define them graphically. That's a vector. Vector is just an arrow in this graphical representation which has a magnitude, which is represented by the length of the arrow. So this will be a vector of smaller magnitude, smaller magnitude, smaller magnitude. And then those arrows also have direction. So this particular one is pointed in a particular direction, this vector points in another direction. So they can share the same magnitude or they can share the same direction. So basically a vector has two main properties: magnitude and direction. Which means that if you would like to define them, you always have to define those two properties. If you only define one, you're not defining a vector. Most outdoor physics concepts can be represented by vectors. So concepts such as displacement, velocity, acceleration, force, momentum, all those physics concepts can be represented mathematically by vectors. So when you are given a problem and you're being asked to calculate the acceleration of a particular particle, you will always need to define both the magnitude, let's say 2 meters per second squared, and its direction, towards the east, towards the west, or you will be using vector notation in the I direction or a j direction. Okay? So keep in mind, a vector is being defined by two properties, magnitude and direction, and you always, 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 always need to define both. Yes, you can switch screen if you want. We have 1, 2, 3, 4 screens. If you those screens are small, so I might start in one screen and I might jump to another screen. If you feel the need as I'm talking to review previous slides or previous screen, please stop me and say, yo, can you show back slide number 4, slide number 2, or the previous one? And then we can go back. Okay? That's not a problem. What I'm asking is, as I'm using the board, please don't switch it on me. Like that. But other than that, it's all good. Just let me know. Okay, so this is a vector. Let's say if I take another vector and I draw it like this. The length, obviously, is the same, but the direction is opposite, right? This vector is going from here to here, while this one is going from here to there. So direction have a starting point and an ending point. So obviously, this vector is different than this one. Vector notation, we put a minus sign to represent the direction, in this particular case, in one dimension. The way that we write vector mathematically is by putting an arrow. So this is the big difference between a scalar. This statement right there is entirely wrong and inaccurate. This is an equal sign, therefore everything on the left hand side must be exactly the same as everything on the right hand side. Now on the right hand side I wrote a vector because I put an arrow on top. On the left hand side I didn't put an arrow, therefore it implies that this is a scalar. A scalar is just a number. 1, 2, 3, 1.2, minus 0.2, minus 2, minus 3. A with an arrow on top is a vector. So those two guys are totally different. So you need to be very careful as you write your mathematics that you are following the rules. I will check your math, and I'm pretty anal about vector analysis and vector notation. So make sure you spend a lot of time on this. Run them correctly. Okay? Okay, so let's say I have a vector that points in this direction. Let's take an example where I am sitting here in a 2D plane and I want to move to this position. So as I'm in position A and I want to go to position B, I'm trying to explain to someone, okay, I want to go from A to B, so I want to go over there. So I'm pointing towards the B direction, so that everybody knows my initial position and my final position, where I'm going. Now I could go from point A to point B in infinite ways. I could go along a straight line following my vector, or I could go through point C, and then I could go through point B. Right? So I could use path 1, or I could use path 2 plus path 3. Right? So let's say if I assign a vector name for path 1, I'm going to call it vector A. I'm going to assign vector B to designate my path 2, and I'm going to assign vector C to designate path 3. Then I can write A as B plus C. This equality is true because I'm starting at the same point and I'm ending at the same point. Okay? Whether I take path 1 or 2 plus 3, what's common between those two is my initial and my final, and that's all I care about. Okay? So I am able to decompose a vector into the sum or the superposition of two vectors. Similarly, I can do it 1, 2, 3 vectors. So if I call this D, I call this vector E, I call this vector F, then I can also write that vector A is D plus E plus F. I just took a different path. And if A is equal to B plus C and A is equal to D plus E plus F, then automatically B plus C is equal to D plus E plus F. Although vector B is not equal to vector D individually, so it's only the sum that's equal. Okay, so I can decompose a vector into the sum of an infinite number of vectors, and you choose how you want to decompose it. The nice thing is that we can. So what we usually do in this class is we decompose a vector, but we decompose it such that it makes our life easy. For example, instead of decomposing my vector A into two arbitrary vectors B and C, I'm going to decide of what we call a coordinate system, which I will call X and Y. And I will break up my vector A, or decompose my vector A into two vectors such that each vector will be aligned along one of my axes. So, for example, I can decompose vector A as one vector B, which has to be along the X, and another vector C, which will be along the Y. Okay, again, you don't have to, but we usually do this to make our life easier. And the reason why it will make our life easier is because if I decompose a vector into the sum of two vectors which are perpendicular to each other, then I recognize nicely a right triangle, which allow us to use all those trig identity that we've seen in Math 140. Okay? So before we complete this, let's review trig identity. If you have a right triangle and the hypotenuse is A, this is B, this is C, then we know right away that there is a relationship between A, B, and C, which is A squared is equal to B squared plus C squared. Okay? Hopefully everybody is recognizing this. Similarly, if I introduce an angle, say theta, then I can use the relationship that exists between A, theta, C, and B. Right? And there is a bunch of them. There is one that tells us that A times cosine theta is equal to C. Similarly, A sine theta is equal to B. Right? Everybody's recognize those equations? If not, let me know. Okay, so far so good. And then once I have those two equations, let's say this is equation 1 and equation 2, then I can divide those two equations, right? And then I end up with B divided by c is equal to tangent theta. The a will cancel out. So now I am able to relate the angle theta with just b and c. Similarly, if I square equation 1 and then I square equation 2 and I decide to add them up, then I will end up with equation 3. Okay? As I square equation 1, I got a b squared, and on the other side I got a squared and sine squared. As I square equation 2, on the right hand side I have c squared, and on the left hand side I have a squared cosine squared. And if I add those two equations, all I'm doing is adding everything on the right hand side, which is b squared plus c squared. And then I'm going to add everything on the left hand side, which is a squared cosine squared plus a squared sine squared. And on this step I can factorize the a squared and end up with a squared times cosine squared plus sine squared. And we all remember that cosine squared plus sine squared is 1. Therefore, we end up with a squared. Okay, I got you, Rameda. Yes, I will apply this remainder of trig into our previous examples. So, is everybody okay so far? Is that a okay refresher from trig? This is the reason why we want to decompose two vectors into two perpendicular ones. Because look, now I can do this. One vector, another vector, and another vector. So now I can find the relationship between those three vectors. Okay, so let's go back to our previous slide. Now that I have my right triangle, let's say I'm going to decompose A into a vector called, I'm going to call it AX, to remind me that this is the component of vector A along the X coordinate axis. Similarly, my second vector decomposition will be called AY, to remind me that this is the Y component of vector A along the Y. And now I can remind myself, oh, I know the relationship between AX, AY, and A. If I put an angle right here, then I know that vector A is related with vector AX by, by this relationship. And I'm sorry, I made a mistake, no vector. So now I can relate the magnitude of all my vectors. I already know the directions because I decided to have AX in the X direction, so I know its direction. I also know the direction of AY because I chose to have AY in the Y. So I know both directions, that's no problem. What I can do now by using the relationship that we've just seen is I can figure out the magnitude of those decomposed vectors, AX and AY, in terms of the given one, A and theta. Okay, and similarly I can do A sine theta is equal to AY. And similarly, the magnitude of the vector A squared is equal to the magnitude of the vector AX squared plus the magnitude of vector AY squared. Okay? So, now I'm ready to write my vector A as the sum of two vectors AX and AY. Okay? So I have decomposed the vector A with two vectors, and I decided and I chose to pick those vectors with a known direction. One will be in the X, one will be in the Y. Okay? Questions so far?